Good morning. I made a mistake. I don't know why, I don't know which way, but obviously I made a mistake. Because in the lab you have very strong problems to set up your circuit. I have to design and mount and to measure it. And I don't understand why, because I know that it's a long exercise, that one is not easy, but usually about half of the groups in the lab have succeeded to have the circuit working, etc. Don't know what happened this year. Probably didn't motivate you enough. Next week we will have lab, and this time you will mount the same compensator that you already designed on the real board, the board we already used with the bulk boost, and we will use that board on in first loop conditions. That is easier, I mean it's faster, because you have just to mount your components, the compensation components, R and C's on the board, and that's it. So next lab will be easier from the mounting point of view. It will be a little bit more difficult to measure because you will have an actual real switching converter, and this converter makes a lot of noise. So you will have noise, so you will see on the scope your trace, and your flash will be very thick because you have ripple on top of it, but you will see what happens. So next Tuesday you will just mount the compensator that you already designed on the board. It means just taking the R's and C's that you designed and mount on the board. Should not be difficult. I'll put this afternoon online the instructions for next lab. Okay? So last time we arrived to design a multiple output flyback converter, something like this. And we found we found all the stresses for these components. We found all the parameters we need to specify to get these coupled inductors, because we need to specify a P, the ratios, etc. We did it. I think we also found the values for all the components, at least the stresses. How much was this capacitor? It's about 1.5 millifarad.
C out 1?
Yeah. Yeah, 1.6, but 1.6 is not a normalized factor. So let's look for a 1.5 millifarad. And here,
100 micro. 100 micro.
100
micro.
Okay. Now we have to decide where to take the feedback, what output voltage to measure to send it back to the feedback control, and how to design the controller, how to design the compensator, because this time we have a flyback. There is this multiple winding magnetic device, and we have multiple outputs. So, first, from what we already discussed this, from what output do we take feedback signal to go back to the controller? In general, when you have multiple outputs, that is general rule, you take the feedback from the highest power out. This output is designed to deliver 5 watts. These two outputs are designed to deliver 1.2 watts each. So probably a good idea is to take the feedback from here. If you take the feedback from one output, any output, and now I am over here, but the same is if you take this output from that output. If you take the feedback from one output and you change the load on this output, the feedback keeps, the feedback is a good feedback because you designed it, and it keeps the output voltage constant, stable. This, just a few transients you can have, but then the DC value goes back to the right value. But if you increase the load, I mean the resistance over here decreases, what happens due to the parasitic leakage inductances? When the load here takes more power, the output voltage VO2 and VO3, they increase. Because when this decreases, the controller sends more energy into the magnetic component, and this energy should go, if everything was ideal, should go all to this output. But a little part of this extra energy goes also to the other two. Here, instead of having, let's say, 12 volts, the voltage can go up to 12.2, 12.5 volts also. So you change this load, voltage over here does not change, voltage over here changes. You increase the load over here, you take more current from here, these voltages go up. And if your resistance increases, these two voltages go down a little bit. This is the so-called cross-regulation problem. And the opposite happens if you change this load. If you increase this load, you take more power, this voltage does not move, but this voltage decreases a little bit. This is due to the fact that these secondary windings are not perfectly coupled to each other, one to the other. There is some leakage inductance, and this leakage inductance makes this effect on the current waveform that I told you last time. It's not a real triangle, it's a triangle with some bumps. And you have this cross-regulation problem. One extra consideration. If you have a very strict, like in this case, ripple requirements, the output, you can go for a large capacitor. That would not be a good idea because of cost, because of slow response, because a large capacitor moves down the pole, etc. In some cases, if you need to have a very quiet, a very clean output voltage, or a clean output voltage, and you don't want to use a large capacitor, what you can do, there are two possible solutions. One solution is to have here a so-called post filter. You put a small LC filter, an extra LC filter, that removes some part of the wrinkle that this capacitor was unable to remove. And it was unable to remove because you didn't want to buy it so large, so expensive, so bulky, etc. So one possibility is to add a post filter. This post filter has just to filter around the switching frequency, not low. In any case, even if you put a post filter over here, it's better to take your feedback from this point. Because if you take your feedback from this point, you add two extra poles inside your loop, your feedback loop, and that would bring in some instabilities. It will be more difficult to compensate, etc. That is one possibility. The other possibility, if you want a low noise output voltage, is to design your secondary winding to give you more voltage than you need. You want the 5 volts very clean, well, you design this winding to get 7 volts, for example. And then you put here a low voltage, a low dropout, low voltage dropout regulator, linear regulator. You waste some power, but you get a very clean output voltage. Okay? That's not our case, and it will not be the case in your exams. So, feedback from here. And now, what about these arms? What do we do with these arms? Do we have to consider them? Sure, because those are volts for this flyback converter. And if you remember how a flyback and indirect converter works, you know that when the switch opens, all diodes at the same time, more or less, start to conduct. That means that all these windings are connected to their load, and all these windings are in parallel passing through the magnetic core, the magnetic current. Well, they are not really in parallel. You cannot take this capacitor and move it over here in parallel. You cannot take this capacitor or this load and move it over here in parallel. But you can move this capacitor to the first output where you are taking the feedback from, using the turn ratio of the two windings. We determine this turn ratio, so we can take this capacitor and move it over here in order to get only one equivalent output, as if it was passing through a transformer. Actually, it's passing through a transformer. What we want to do in order to find the transfer function and to design the compensator is take these two loads, these two capacitors and these two resistive loads, and move them in parallel to the first one, to the first output, where we are taking the feedback from. And we do this just moving resistors over here, loads over here, capacitor over here, using the ratio. How is resistance multiplied by when you pass to a transformer? You have the ratio square. What was the minimum value for this resistance? Because remember, for a flyback converter, for a buck boost converter, the most critical condition for design to have the stability is to have the minimum load resistance. That was the worst case. So how much was the minimum load resistance? It is something like output voltage divided by maximum current. R min equals V naught divided by I max. And you have to do this for each output. For the first one we had 5 volts and
2 amps.
2 amps. So the resistance is 2.5 ohms. What about the other two outputs? This output was 12 volts divided by 100 milliamps. It's 0.1 amps equals 120 ohms. And what about this one? Same story. 120 ohms. Now we have to take these two resistances, not resistors, and move them in parallel to the previous, the first one. How much was the turn ratio between the secondary winding and the first secondary winding? How much was NS2 over NS1 or whatever we evaluate? This and this is 2.4, a little bit less.
2.27.
2.27.
Yes.
NS2 over NS1 equals 2.27. Do we have to round this up to an integer number?
No.
No, because this is a ratio. That must be a rational number. And you have to hope to be able to get the two number of terms, whose ratio gives you this. We have here, let's say, one term, we have here 2.27 terms. This is the ratio, NS2 over NS1. And when we go this resistance from a high number of turns to low number of turns, we decrease the voltage because there are less turns. And if we decrease the voltage, we increase the current because it's transformer. That means that when this resistance, that is 120 ohm resistance, moves over here to a lower voltage, its value increases or decreases. You go to low voltage,
So it decreases.
it decreases. You have to multiply the resistance times the turn ratio in the same direction you are going to. So, let's go over here. The first output will just be that resistance is 2.5 ohm. That is the original one. Then there will be a second one that is 120 ohms multiplied or divided by 2.27 squared. Divided by 2.27 squared. Remember, when you go towards the low voltage, you need a lower impedance to get the same power. And so it's divided by 2.27, and if instead of NS2 over NS1 I gave you NS1 over NS2, you have to multiply by that factor. 2.27 squared is about 5 5.1. And so this is 120 ohms divided by 5.1. That's easy. 120 divided by 5 is
24.
24. But this is not 5. This is a little bit more than 5. So the result will be a little bit less than 24. Point 1 is 2% more than 5. The result will be 2% less than 24. And 2% less than 24 is half an ohm, so it will be 23.5 or so. How much is it? 23.5 ohms. And then there is a second secondary that has exactly the same effect. So we will have here another 23.5 ohms resistance. This is the equivalent resistance where all your loads have been moved to the first output. Not the first output because it's the first, but the output from which you are taking the feedback signal. And what about capacitors? Capacitor is the same story. The impedance of a capacitor is translated, is modified, is changed exactly as the impedance of a resistor. But the impedance of a capacitor is 1 over Sc. So if instead of using the impedance we want to see what we want to see, the capacitance is treated the other way. So instead of dividing by the turn ratio squared, you have to multiply by the turn ratio squared. That means you have to take the turn ratio backwards. Not where you arrive divided by where you are starting from, but where you are starting from divided by the number of turns of where you arrive. And here we have 1.5 millifarads, and there will be here a first capacitor, equivalent capacitor that arises from one of the two 12 volts output. That is 100 microfarad times 2.27 squared. Oh, what are the dimensions of this 2.27? Dimensions. And this capacitor will be 510 microfarads. And then we have a second capacitor, equivalent capacitor, that is the, let's say, this one moves through here, passing, while the move through here, passing to the magnetic component, and modified using the square of a turn ratio. Remember, resistances, when you go in this direction, is where you arrive, the number of turns where you arrive divided by the starting point. Capacitors is upside down, and the turn ratio squared. So, our output will be our equivalent output, and that's not the real output. The real output is not this one. The real output, we have 3 outputs, but the equivalent circuit will be something like, here we have 2.52 millifarads, and 23.5 parallel to 23.5 is 12 parallel to 2.5. 2.5 is about 5 times smaller than 12 point whatever it is, 12 ohms.
2.2.
And so the result will be about 1/6 less than 2.5. 1/6 of 2.5 is 0.4, so it's 2.1, let's say. Not close enough. 2.06. Okay, made a mistake, sorry guys. I told you at the very beginning when you were not yet here. Today I forgot my pocket calculator, I forgot my slide rule, so I am unable to do calculations. 2.06 ohms. What kind of a converter are we designing? Flyback. DCM or CCM? DCM. Flyback has the same transfer function of our boost, changing just the gain. So that my V0 over VE is just something like this. VE is the error signal coming out from the R15, the voltage R15. And you know what are the frequency of this pole and this zero. This zero frequency is
Yes,
due to the ESR capacitor. This is the reason why I told you pick the same zero frequency for all the capacitors. So when you move them through the transformer, through the couple wires, you get three capacitors in parallel with the same zero, and you still get the same zero. If you change the, you say, oh, this one has a zero at 10 kilohertz, these two capacitors have a zero at 3 kilohertz. Here, you start to have something strange, and there are 0 poles all crowded together here. And it's not a big difference, but calculations become very boring and long. When I have this case and reality to have different technologies, I use SPICE, because just solving some analytic stupid calculations is a waste of time. Here, 10 kilohertz. Because we decided to use capacitors having a 10 kilohertz ESR zero. What about this pole frequency? That is the pole of a buck boost converter, DCM. How much is the pole of a buck boost converter, DCM? Better if you remember that.
it was the one that doesn't depend from the load, if I remember. So,
1 over pi RC. 1 over pi RC. How much is R? 2.5 ohms, because we are taking the feedback from the first half. No, we have to use the equivalent resistance, that is 2.06 ohms. How much is C? 2.52 watt. Okay, 2.5 times 2 is 5, really? 5 times 3, 15. The reciprocal of 15 is 0.06667. Then we will adjust the result, just to have an idea what we are. And we have no units, milli. This milli moves up, becomes kilo. So 0.067 kilohertz. That means if I multiply by 1067 hertz. Well, this is not really true, because this is about 1%, little bit less than 1% more. This is 3% more, so we are 4. Pi is about 4-5% more than 3, so we have another 8-9% less. So the result will be 8-9% less than this. 8 times 7 is 56, so 5 hertz less, something like 62 hertz. 61.31. And that. Sorry guys, I don't have the calculator again. 61.3 hertz. If you believe it's Santa Claus, because believing to this number is, the other way around. Believing in Santa Claus is more scientific than believing in this number. This number depends on the tolerances of a capacitor. And the capacitor tolerances could be easily plus minus 20%. We derived this expression under some conditions to make our calculation easier. That means no losses, no parasitic inductances, etc., etc. So this is just a number that could be easily from 50 to 70, minimum, 20% out. 20% off the new mark, but this is a reference point for us. What about the DC gain? We derived it a couple of times ago, a couple of lectures ago. DC gain changes if you are using voltage mode or current mode. The expressions are slightly different. If this is voltage mode, and this is the reason why I put here VE error instead of V control, voltage mode equals plus 1 over the gain of voltage mode, 1 over V triangular times the triangle sawtooth peak-to-peak amplitude, that means the gain, this is basically the gain of PWM modulator, times R over
F switch times L.
We derived it, didn't we? Say yes. This is 1 over. This is a number that they give you. And they gave you 3 volts. Times the square root of RL, the minimum load resistance, because the minimum load resistance is the resistance giving me the worst case, the worst condition for stability. And we discussed it while analyzing the buck boost model. So there is 2.06 ohms. It's a pain to write down 2.06. 2.1 is even too precise. Divided by 2 times switching frequency 200 kilohertz, and switching frequency 200 kilohertz depends on your controller IC, on the capacitor, and the resistance. And another time you can have 20% of tolerances of components and the IC. Times LP was 8.9 microamps. 8.9 microamps.
The result is minus 12 dB.
It's too low.
The
Thank you. Then we calculate the minimum or maximum. Maximum. So this is 32 volts plus 32 wasn't
30 minutes.
Yeah. 2.2 is 0.4, 0.4 times 9 is 3.6. 2 divided by 3.6 is
0.
about 1/2.
0.6.
Square root of 0.5 is 0.7, but this is a little bit more, 0.8. How much is this square root, please?
that's all. 864.59.
What? No.
No,
Me.
0.8?
0.9.
0.9. Okay. So we have 32 divided by 3 is 10, 11. 11 times 0.9 is 10 times. Resistance divided by resistance dimensionless, volt divided by volt is volt divided by volt is dimensionless, and this is okay. Okay. My DC gain is 10 times. With minimum load and maximum input voltage, because this is the worst case for stability. What about if we use a current mode compensator? Current mode compensator has exactly the same shape. This is V naught over V control, and the pole and zero are exactly the same position. So this is 2.1 hertz, and this is 10 kilohertz. No, not 61.3 hertz. I'm curious to know where is this 2.1 coming. Oh, there was the resistance. 61.3 hertz. How much is this gain for a current mode controller? Something like 1 over Rs times square root of R load times switching frequency times LP divided by 2. And we derived this last time. That's true. Didn't we derive it? Yeah. And we use equal to, I forgot this, 0.22 ohms.
2.0.
No, RS.
0.22.
0.22 ohms. Times the square root of 2.1 ohms times 200 kilohertz times 8.9 microfarads divided by 2. How much is this?
1.5.
0.2 times 2 is 0.1 times 2 is 0.2. 0.2 times 9 is 1.8. Divided by 2, I already divided this division, so the square root of 1.8 is 1.35, something like this. And this is the resistance, because we have frequency times inductance gives me a resistance, times another resistance is a resistance squared. The square root is a resistance divided by a resistance is dimensions. And our gain turns out to be, it will be 1.34 ohms divided by 0.22 ohms. 6.1. This gain equals 6.1 times, not dBs. There is a trick to check if this result is okay. This result is right. And this gain is V naught divided by VRS at maximum output. How much is VRS? What did we design for?
1 volt.
For VRS? It was 1 volt. So 5 volt divided by 1 volt is 5. Well, we got something more. Why?
Because VRS max for us is 0.8.
We, instead of using the exact resistance we came out with from 1 volt divided by IT, we reduced this resistance to a normalized value that was smaller than what we obtained. Instead of 0.24, I think it was 25 ohms, we went down to 0.22 ohms, because we want to be sure that no matter what, we can deliver the right amount of power. And so if we reduce the RS value, we also reduce this voltage, and this ratio becomes larger. Not too much larger. 6.1 instead of 5. That's okay. 6.1 is the number to use. If you want to be very cool, you can say, okay, this is the gain from the comparator to the other. But we could still divide it by 3, because I told you that inside many compensators circuits, IC controllers for current mode systems, there is a voltage divider that divides the voltage coming out from the op-amp by 3 in order to adapt the large dynamic that an op-amp would like to have, and the small voltage on the resistors, sensing resistor that you want to have to avoid too high losses, too large losses. So if you want to still to divide by this number that is inside your IC controller, not all IC controllers have this factor. In some cases you have to multiply it by 3 and other factor. But if you want to go for 2.1, it's okay with me. Just tell me what you are doing in your exam, in your written exam, and I accept all the solutions. Okay? Our transfer function that we have to compensate is this is what we have, and here we can have either 2.1 or 10, depending on your time. Yes. This is for current mode, this is for voltage mode, and in both cases, more or less, we want to obtain something like this. This is my final key. And the only number I have to specify for this loop gain is solar frequency. How much do we take? Do we design this crossover frequency?
Depends from the switching frequency.
It depends on switching frequency. Switching frequency divided by 6, divided by 5 if you are in other mode, divided by 10 if you want to be very safe and slow.
Excuse me, can you repeat why we have to divide 6.5?
You don't have to divide, but in some cases, depending on what IC you use, you have to divide by 3 because I think if you go back about a couple of weeks, current mode controller, we have a type 2 compensator, VRF, reference voltage, RDC, and this is V0, and you go from this point to the comparator, and the comparator is something like that. From here you get IL times RS, and here you have your reset, set, clock. The output Q goes to control the switch, to command the switch, to open and close the switch. This is the controller for a current mode. Are we up to this point?
Yes, I remember why. Because we introduced a voltage divider.
Yes, and I told you a moment ago. IL times RS cannot be too large, otherwise I waste power. Usually it is around 1 volt or less. An op amp working around 1 volt is a pain in the neck because it has no dynamic, there's too much noise. At least we want to hear from 1 volt to 4 volts. And so we put here a voltage drop of 1 volt in such a way that this op amp, even if its output is, let's say, 0.7 volts, the output here will be 0 and nothing happens. And then we put here R to R divider, voltage divider. So this op amp can work from 1 volt to 4 volts. It has 3 volts of dynamics. This goes from 0 to 1 volt. That is the voltage we want to adhere. That is a possibility. The other possibility you find somewhere else, in some other controllers. You have this connection direct. So the comparator works at 3 volts. But at this point, you have an amplifier that multiplies the input signal by 3. In this case, it's like having a resistance value, RS value is 3 times as much. So in your calculation, you have to put 3 RS. The other case, you have to divide by 3, the result is exactly the same. Did I answer? Yes. Did I already tell you in the past this stuff? Yes. What is divider at least? Yes. Okay. I forgot what point it was at. Designing the loop gain, and the only number we have to take here is the crossover frequency. Could be 1/5, 1/6 of the switching frequency, 1/10 of the switching frequency if you want to be very safe and slow. Our switching frequency is 200 kilohertz. Let's try to go for 20 kilohertz. This is 20 kilohertz. This means that our compensator circuit must provide me, which again is something like this. I put a 0 from my compensator on top of my pole, a pole of my compensator on top of my 0, and a pole in the origin. Why do I want a pole in the origin? High DC gain giving me very small DC error. Type 1 system. Type 1 for control guys, not for us. I know this 0 frequency, 61 Hz. I know this whole frequency, whatever it is, kilohertz, 10 kilohertz. I just need to find this DC gain. And this DC gain is given by how may I find that the DC gain? This DC gain is just the distance between these two curves.
Starting from FC, we can use the rules of dividing the high gain by the lower gain.
All those slopes are 20 degrees per decade slopes. So high gain divided by low gain equals high frequency divided by low frequency. And I can use any 2 points in this parallel track, in these parallel tracks, any 2 points over here where I know the gains, and I take the ratio of these 2 points, the gain of these 2 points. And the most convenient point is this one, because I already know the DC gain of my plant, of my power stage. I have just to find how much gain I need for my compensation, and the ratio between this gain and that gain gives me what I have to provide. If you think in dBs, the difference between this gain and this gain in dBs gives you the gain in dBs of your compensator in this flat region, plateau. 20 kilohertz is my crossover frequency. How much gain do I need for here? High frequency divided by low frequency equals
I gain.
high gain divided by 1. Low gain is 1. And so this gain is given by 20 kilohertz divided by 61.3 hertz.
326.
That is 326 dBs?
No.
No, this is the fact. How many dBs are 326?
Six, 51.
50?
3.27. 50.
50? Okay. This is the gain I have over here. How much gain does the tank in the power converter provide me? Well, if I am in voltage mode, the gain is 10. If I am in current mode, the gain is 2.1. In your exam, in your design, just pick one solution. I don't want a double solution. I want just, if you want to go for current mode, go for current mode. If you want to go for voltage mode, go for voltage mode. But there are no differences in the flyback. Which one do we use? Current or voltage? Let's go for voltage mode. That's exactly the same. If we go for voltage mode, the gain we need over here is 326 divided by 10. That is 32.6 times. And now we know transfer function we have to implement to synthesize, and the circuit giving me that transfer function is something like this. R2, C2, C1, R1, here there is V0, VRF. How much was VRF? 2.5?
Yes.
2.5. And RDC. Four components to find. Oh, components, not components. Components, please. Yesterday, no, on Wednesday, there was a graduation from a few students, and I heard of so many components that I wanted to scream, no, it's components, not components. Seemed a bad thing to do during the graduation discussion, so. But please. Oh, by the way, the other exam is in English. I want to grade your English for sure. As long as I understand you, that's fine with me. Because it's not an English exam, it's a power electronics exam. And I met many engineers around the world that have a very horrible English. But as long as you don't understand them, they are telling you good things, that's okay. If your English is very good, sometimes I correct your pronunciation as far as I know, but only because your English is very good, you are not having problems with it. And usually after the exam. Okay. 4 components, 1, 2, 3, 4. Well, RBC is after. And 3 equations, pole, 0, gain. We have 1 degree of freedom that we use to
because we fix one capacitor.
we pick one capacitor. That is basically just a rule of thumb. It's not something carved in stone. And we can pick C1, a reasonable value. That is from 68 to 50 picofarads to 500 picofarads, something like this. I will pick here 100 picofarads, and as usual you are forbidden to use this value in your exam. Otherwise, I will have a lot of same components, same calculations boring. Do you remember the equation for this stuff? We have the closure pole, the pole at 10 kHz, Fp. Pole occurs and this capacitor has the same resistance, same impedance as this resistance. So it's Fp equals 1 over 2 pi R2C1. That means 10 kHz is equal to 1 over 2 pi 100 picofarad times R2.